Whether it's someone swimming in the ocean, or an apple falling from a tree, or a satellite going around the Earth, how do we describe motion that we see every day? When describing motion, the first thing we need to consider is position. This describes where an object is. To describe where an object is, we describe it relative to some origin. Here are some artists' impressions of what the Milky Way looks like. The Milky Way is a bar spiral galaxy. So here we have a central bar with the spiral arms spiraling outwards. So this is like a on-top view of the Milky Way. Side on, we see a central bulge in the Milky Way and then a flat disk where the arms of the Milky Way lie. The position of stars within our Milky Way are measured by the distance they are from the centre of the Milky Way out along the disk. Then they're measured how far above or below the disk they lie. Then finally, the angle from the sun to the position of the star is measured. So in this sense, the origin is the centre of the Milky Way, but we also have to use the sun as a reference point as well, because we can't be in the middle. It makes it a little bit challenging. However, there is no preferred origin in this angle measurement here. We could define the position of stars relative to a compass in the middle or another star further out. So this idea of origin is always relative. We get to choose where the origin is. Looking at some simpler examples, we might choose the origin of a swimming pool to be the starting position of a swimmer. Then we could describe the position of the swimmer by simply stating a measurement like 25 metres. On a soccer pitch, describing where the ball is along the pitch, it might be more convenient to use the origin as the centre line. Then, to differentiate between the ball being in one half compared to the other, we could use directed numbers, so indicate a positive and a negative direction. Or we could describe the position of the ball using perhaps an east or a west direction. So in this case, I could describe the position of the ball as being 20 metres east or plus 20 metres if I'm using directed numbers. Moving into 2 dimensions, we could describe the position of the soccer ball using our compass system. We'll look at situations where we move around along the surface of the Earth and we use this system to describe position, but also direction of travel. Now let's have a look at some motion where the position is changing. Here we see the swimmer completing 2.5 laps of the 50-metre pool. There's 2 different ways in which we can describe this motion. The first is the total distance travelled. This is equal to the length of the path from the start to the finished position. So shown then orange up here, we see the length of the path equal to 3 lengths of the pool, being 150 metres. This is what we call a scalar quantity because it requires a magnitude and no direction to describe. Another way of describing this motion is by using the term displacement. This is equal to the change in position of the swimmer. Here, the change in position is from the 0 metre mark to the 50 metre mark. So their change in position or displacement is 50 metres to the right here. We needed a direction to describe this change in position because if another swimmer started at the opposite end of the pool and then finished over here at our origin, we'd say their displacement, the change in position, was once again 50 metres, but in the opposite direction to the left. So displacement is a vector quantity, meaning that to fully describe a displacement we need a magnitude, like the 50 metres, and also a direction. Now the displacement of the swimmer is independent of the path taken. That's because the swimmer could complete one lap and have a displacement of 15 metres right, or 3 or 5 or 7 laps and still have the same displacement. So this change in position, it doesn't matter how it occurred, just start to finish. Next we want to describe how quickly an object is moving. There's two very important ways that we can do this. One represents an instant in time, and we'll call that an instantaneous measure. And the other one represents a change in a bigger period of time that we'll consider an average. Now, instantaneous speed is the rate of change of distance, whereas instantaneous velocity is the rate of change of position. Now, there's only a minor difference here, and that is instantaneous speed is a scalar quantity, whereas instantaneous velocity is a vector quantity. We need to state a direction for the velocity. So if you're riding along on your bike, you might look down at your bike computer and it will tell you that you are travelling at, say, 26 kilometres per hour. So notice here that we have a rate, kilometres per hour. What this is your instantaneous speed. At that moment in time when you glanced at your bike computer, this is how fast you were going. To change this into an instantaneous velocity, we just need to add a direction. Note that on the way back, you could travel at the same instantaneous speed, however, the direction will be different. So the instantaneous velocity includes more information. Now let's look at average speed and average velocity. So we go for a ride, and then when we get back, we look at our trip computer and it tells us we covered 10 kilometres in 30 minutes. This means our average speed is 20 kilometres per hour. However, our average velocity is very different. It's actually 0 kilometres per hour. Why? Because our change in position over the trip is 0. Our position hasn't changed. So, average speed and average velocity are very different, and you need to be careful here. So average speed represents, on average, how fast were you travelling along your path, whereas average velocity represents, on average, how fast were you travelling along your change in position. Let's consider a running track where one loop is 400 metres, and I've shown two positions here. This is going to be our start position, and then halfway around the track is our finish position, 200 metres along this path, and it's only 50 metres between these two measurements in a direction that is due north. A running coach tells his athlete to run out as fast as possible over 1.5 laps. Meanwhile, knowing that they'll tire out, he jogs around at the one speed. In this scenario, we see the instantaneous speed of the athlete is changing, whereas the instantaneous speed of the coach is not. It's always the same. However, the instantaneous velocity of both of these athletes, coach and the athlete, changes as they go around a bend because their direction of travel changes. Now their average speed was the same in both cases because they completed the 600 metres, the 1.5 loops, in the same amount of time. Also, their average velocity was the same because they experienced the same change in position from start to finish over the same time. Now let's consider the scenario where the athlete is given the same instruction, but now the coach is on a walking stick and needs to walk directly to the finish. In this scenario, they still have the same average velocity because their change in position is the same over the same time. However, their average speed is clearly different because the distance they travelled in that time is different. So the key points here, to move from instantaneous speed to instantaneous velocity, all we need to do is add a direction. However, Average speed and average velocity are very different. One takes into account the total distance divided by the total time, whereas average velocity is the displacement, which is the change in position over time. When an object changes how fast it is moving, we call this acceleration. This year, we won't really look at too many examples where the instantaneous acceleration of an object might be different to the average acceleration. You can imagine in a car when you accelerate rapidly, initially you might undergo a very large acceleration, but then as you're changing gears, perhaps that acceleration might drop off. And what you might find is the acceleration you get changes over time. And then the average acceleration would describe the total change in velocity over time. And these two quantities can be different, but we won't really look at that this year. But what you do need to have a good understanding of is what acceleration is. To do so, you really need to understand the units of acceleration. There's 3 different ways in which we can write the units for acceleration: ms to the minus 2 or m/s squared. However, it is this third one that is my favourite because it makes the most sense to me. So let's consider an acceleration of 2 meters per second per second. This tells me that the velocity of an object is changing by 2 meters per second per second. It is important to recognize here that acceleration is a vector quantity, so let's put a direction, say north. So what this might mean for an object, say starting at rest at t equals 0, well then after 1 second the object will be travelling at 2 meters per second. After 2 seconds the object will be travelling at 4 meters per second. Then after 3 seconds, the object will be travelling at 6 meters per second. In this scenario, the acceleration represents a speeding up of the object. That's because the acceleration is in the same direction as the motion of the object. However, this doesn't have to be the case. If we consider an object at t equals 0 travelling at 10 meters per second south, then if it was undergoing the same acceleration of 2 meters per second north, after 1 second it would have a velocity of 8 meters per second. Then, after 2 seconds, it would have a velocity of 6 meters per second south. So in this scenario, an acceleration of 2 meters per second north represents a slowing down of the object because it's travelling south. Let's have a look at your information sheet to see what you're given. We see here that displacement is given the symbol S, acceleration is A, and then we have initial and final velocity. You also get given the SI units, the standard units you should work in meters, meters per second, and meters per second squared. You'll note here that the only formula we have so far is for average velocity. You need to remember that average speed is distance on time. You also need to remember some conversions for time. It is also important that you remember how to convert between kilometers per hour and meters per second. This is best done by simply remembering that to convert, we either times or divide by 3.6. When making this conversion, please do a quick check. Let's say we're converting 100 kilometers per hour and you thought we had to multiply by 3.6. We'll get an answer of 360 meters per second. I'm hoping that you understand that this is completely unreasonable. If you're on the highway going 100 kilometers per hour, you're not travelling 360 meters each second.